We'll look at two nonlinear models of differential equations, although there are more than that, and you'll see them in the homework. But these two are the ones we're going to look at in detail. The first one is logistic growth. This model applies more appropriately to large populations or when environmental factors inhibit growth. That is to say, exponential growth works for bacteria in a petri dish, but even at some point, they will outgrow their nutrient supply or the size of the petri dish. But in the wild, if you've got a population of, say, rabbits, there are going to be limitations as to how much food can support them. And then, let's face it, there are wolves that are going to eat the rabbits. If we were to distribute this p here, we would have a term that is negative bp squared. In this model, b is going to be a positive number, and that negative bp squared is called an inhibition term or a competition term. As far as why this model is appropriate, the justification for it starts with remembering what we saw in the previous lesson. If dp dt divided by p equals k, then we have something called a constant relative growth rate, right? The growth rate relative to the population is constant. The logistic growth model presumes we have a relative growth rate that is variable, but still dependent on the population. And this model is dp dt divided by p is equal to f of p. One feature of a logistic growth model is the incorporation of the idea of carrying capacity. If we label that carrying capacity as k, and right now I'm going to tell you right now it's uppercase k. It's to be distinguished from the lowercase k in the previous model, so I'll just make that happen there. If that uppercase k is the carrying capacity for the population, we can think of that as a maximum population that an environment will support. Then the relative growth rate, which is given by f of p, should be 0 when we get to that maximum population. Now denote by r f of 0. So let f of 0 equal r. Then in the simplest case, we can represent f of p using a linear function. If f of 0 is equal to r, that gives us a point on the vertical axis at 0r. And if f of k equals 0, that gives us a point on the horizontal axis at k0. And then in the simplest case, these 2 points are connected by a line segment. So the simplest case would be linear. Thinking about something like y equals mx plus b, if we got f of p, then that would be r minus, now the slope is going to be negative r over k, rise over run, times p. So we have f of p is equal to r minus r over k times p. Then the differential equation becomes, we had dp dt over p was that variable growth rate. Clearing that fraction is going to give us dp dt is equal to p times r minus r over k times p. Relabeling gives us that equation that we saw earlier, which is dp dt equals p times a minus bp. And I just realized I didn't read that at the beginning of this lesson, but here it is. And due to this relabeling, let's note that k is equal to a over b, and this is the carrying capacity. And here I'll give you some images that illustrate what the graph of the solution of such a model looks like. For an initial population above the carrying capacity of a over b, we see the population is going to decline to approach that carrying capacity. And an initial population below the carrying capacity will grow until it behaves asymptotically with the carrying capacity. I also want to point out that this dp dt equals p times the quantity of a minus bp is an autonomous differential equation, of the type that we saw in a previous lesson.